The most intuitive way to think about these different encodings is to think of Huffman codes as trees. So if we have these symbols, we can put them into a tree and see how that plays out for these different encodings. So we have our fixed encoding that we've been looking at. We had our bad variable encoding we looked at, and then we had our prefix-free encoding. So for that first tree, to get to A, it was 0, 0. So you would go down the left, and that's how you find the symbol A. And likewise, if I'm looking for 1, 0, a 1 means go right, and a 0 means go left, so that's where I find the C. For our middle encoding here, to get to the A, we just went left once. To get to the B, we had 0, 1. So this is why this is called a prefix-free encoding. If you notice, A is found on the path to get to B. So we don't know if we should stop at A or if we should go all the way to the leaf to get to a B. It's sort of an ambiguous encoding. Whereas for our prefix-free encoding, we had A, B, C, and D. And I should mention not all of our Huffman codes will look at like this one-sided tree. There's no reason that it has to be like that. Just in this example, that's how it plays out. So in general, if you're processing one of these Huffman codes, you're going to go left on a 0, you're going to go right on a 1, and for each symbol in the entire set of symbols sigma, exactly one node should be labeled with that symbol. And for a prefix-free encoding, all of the symbols must be found at the leaves of the tree. And trees are really just a tool for helping us construct the optimal encodings, and you don't actually have to store them as a tree with pointers or anything in code. And then decoding follows the same exact sort of path. If I find an input of 0, 0, 1, I just go left twice and then 1 to the right, and that should lead me to a leaf where I can pick out the correct symbol. And in coding, I just follow the path from the root down to whatever symbol. So back on this example, if I wanted to encode a B, I know to get there I have to go right 1 and then left once, which gives me a 1, 0. And then finally, the encoding length of a given symbol is the same as its depth in the tree. So let's practice this. Let's start by decoding the string 0, 1, 1, 0, 1, 1, 1. Well, we start at our input, which is a 0. We go left, we've hit a leaf, so A is our first symbol that we've compressed. Now we move on to the next part. We've got a 1, we go to the right, we have another 1, we go to the right, we have a 0, we go to the left. So our second input symbol is a C. We go right, right, and right, 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 and right, and our final symbol is D. So ACD is the sequence of symbols encoded by that bit string. Well, probably the next question on your mind is, how do we choose or design our encoding? Another way to think about that is, how do we come up with the tree? So here's our problem. We have an input set of symbols sigma and their probabilities or frequencies. Either will work. Because as probabilities increase, so do frequencies. So what we want to say here is that if we have a tree T, you can compute the average number of bits needed for any symbol by taking the probability of that symbol and multiplying it by the depth of that symbol in the tree. So this is something we have as input, and this is something that we will sort of construct. We'll construct that tree. So what does that make LT? That's the average encoding length for all symbols. And what we're trying to do is output the tree T that minimizes LT, the average encoding length.